Myself, Dr. Rashmi Saxena. I am Professor Chemistry and I am working in Government MH College of Home Science and Science. Now we will discuss the basic principle of NMR. We know that nuclei are positively charged and nucleus spins on its axis. Whenever any charged body spins on its axis, it will generate a magnetic field. That is to say, it will behave like a small bar magnet. And this nuclear spin quantum number, it is quantized and it is represented by I. The value of nuclear spin quantum number I depends upon atomic number and atomic mass. Atomic number is odd, atomic mass is odd, then the value of I will be half integer. It can be half, 3 by 2, 5 by 2. Example is proton, phosphorus 31, fluorine 19. When atomic number is even, atomic mass is odd, then the value of nuclear spin quantum number is half integer. Example is carbon 13. When atomic number is even, atomic mass is even, then the value for nuclear spin quantum number is 0. Example is oxygen 16 and carbon 12. When atomic number is odd, atomic mass is even, and the value for I is integer. It is 1, 2, 3, etc. Example is nitrogen 14. So we see here that the value of I, that is a nuclear spin quantum number, depends upon atomic number and atomic mass. Spinning nuclei behaves like a small bar magnet. Under the absence of any external magnetic field, the nuclear magnets are randomly oriented in all directions. But when magnetic field is applied, they are aligned in a particular manner. There can be two situations. One, where the nuclear magnets are aligned with the external magnetic field, and the second situation is when the nuclear magnets are aligned against the external magnetic field. The lower energy state is one where the nucleus are aligned with the external magnetic field, and the higher energy state is one where the nuclear magnets are aligned against the external magnetic field. There is a very little difference in the population of two states. Nucleus can have different orientations in presence of external magnetic field. The question is how many orientation it can have in presence of external magnetic field. The number of orientations in presence of external magnetic field depends upon the value of nuclear spin quantum number. For carbon 12 and oxygen 16, the value of I is 0. Therefore, these two nuclei will have only one orientation in presence of external magnetic field. For proton, the nuclear spin quantum number is equal to half. Therefore, it can have two possible orientation. For nitrogen, the value of nuclear spin quantum number is 1. Therefore, it can have three orientations in presence of external magnetic field. Now each orientation corresponds to an energy state of nucleus. You can see here spinning nuclei in presence of external magnetic field. There are two energy states. One is plus half, which is also known as alpha. Another is minus half, which is known as beta energy state. So the energy of orientation for proton is equal to plus minus mu h BO, where BO is the external magnetic field and mu is the magnetic moment of the proton. Value of mu is specific for a particular nuclei. And you see, this is the energy gap between the two levels from minus mu HBO to plus mu HBO in presence of external magnetic field. In NMR, the transition of nucleus from the low energy state to the higher energy state occurs. This transition occurs by the absorption of radiation in the radio frequency region. The energy gap between the two energy levels, we can calculate E2 minus E1 equal to, that is the delta E becomes 2 mu H BO. Now as the magnetic field, the strength of magnetic field we increase, the gap between the two energy level also increases. If there is no magnetic field, there will be no orientation. The different orientation arises in presence of external magnetic field. So the energy gap between the two orientation depends upon the strength of external magnetic field. The spinning of proton under the influence of external magnetic field can be compared with the spinning top, that is the Lect-02. The spin axis of Lect-02 does not corresponds to the direction of the gravitational field. It shows the precessional motion, that is, it rotates in a circle perpendicular to the gravitational field. So we say the top precess, it rotates in a circle perpendicular to the gravitational field. Here in the diagram it is shown that there is a spin axis of the top, and this top is precessing, it is rotating in a circle perpendicular to the gravitational field. Like the top, nucleus also shows the precessional motion, that is, it is rotating in a circle perpendicular to the external magnetic field. In presence of external magnetic field, it can acquire two states, one where the magnetic moment is aligned with the external magnetic field, and this is the low energy state, and another is magnetic moment opposed to the external magnetic field, and this is the higher energy state. We can represent the two states by different names. One name is alpha state. When the magnetic moment is aligned with the external magnetic field, it is known as the alpha state. When the magnetic moment is aligned against the external magnetic field, it is known as the beta state. It is also represented by plus half state. When it is aligned with the external magnetic field, when the magnetic moment is aligned against the external magnetic field, it is represented by minus half spin. N alpha represents the population of nuclei in the low energy state, alpha state, and NB represents the population of nuclei in the higher energy state, that is the beta state. Like the top, nucleus also shows the precessional motion, and it is associated with the precessional frequency. The precessional frequency is the number of complete revolution the magnetic moment vector makes around the applied magnetic field in 1 second. The energy difference between the two energy levels, that is the aligned with the external magnetic field and aligned against the external magnetic field, is given by delta E is equal to H gamma by 2 pi BO. Gamma is the gyromagnetic ratio, and it is constant for a specific nucleus, and for proton the value is 26,753 per second per Gauss. Now we can represent this in terms of frequency also, because delta E is equal to h nu. So nu will be equal to gamma by 2 pi multiplied by this Bo. Here the gamma, 2 pi, these are the constant. So we arrive on an equation that nu is directly proportional to Bo. That is, the frequency is directly proportional to strength of external magnetic field. So a proton which is placed under the influence of 1.4 Tesla external magnetic field strength, it will precess 60 million times per second. That is the frequency of that nucleus which is placed under the influence of external magnetic field of 1.4 Tesla will have the precessional frequency of 60 megahertz. If it is placed under the influence of 2.3 Tesla, then its precessional frequency will be 100 megahertz. And when it is placed under the influence of 14.1 Tesla, then its precessional frequency will be 600 megahertz. So we can see that the precessional frequency of nucleus depends upon the strength of external magnetic field. The third term in NMR is resonance. So what is the state of resonance? It can be defined as when the precessional frequency of nucleus matches with the frequency of electromagnetic radiation. Then absorption of energy will take place and nuclei will flip from the lower energy state to the higher energy state. For example, if we apply 1.4 Tesla of external magnetic field, then the naked proton will have a precessional frequency of 60 megahertz. Now, if we give radio frequency of exactly 60 megahertz, then there will be absorption of energy and nuclei from the low energy state will move to the higher energy state and their orientation will change. If we give frequency other than 60 megahertz here, then there will be no absorption because state of resonance is not achieved. So state of resonance is achieved only when the precessional frequency matches with the frequency of electromagnetic radiation, and the nuclei here present in the lower energy state, they will show the absorption and they will flip to the higher energy state and their spin orientation will change. The population of nuclei in two energy states can be determined by Boltzmann distribution equation. This is the Boltzmann distribution equation where the n upper is the showing that the population of nuclei in upper energy state and n lower showing the population of nuclei in the lower energy state equal to e to the power delta E kT, where T, capital T, is the absolute temperature, K is the molecular gas constant, and this can be modified to this equation h nu upon kT, where h is the Planck's constant. So when we apply 1.4 Tesla of external magnetic field at this magnetic field, there is a very small difference in the population of nuclei in alpha and the beta state. In alpha state has got just 0.001% higher population than the beta state. Now when we give electromagnetic radiation of 60 megahertz, then nuclei present in the lower energy state will show the absorption and they will flip. There can be a situation when the population in the two state, that is the low energy state and the high energy state, becomes equal, and this state is known as the state of saturation, and there will be no further absorption of energy and the resonance signal will fade out. Nuclei present in the higher energy state will lose energy equal to delta E, and they will come down to the low energy state. This process is known as the spin relaxation. Spin relaxation can occur by two processes. One is spin lattice relaxation. The lattice means here is the surrounding. That is, solvent molecules surrounding the nuclei constitutes the lattice, and the delta E amount of energy is released to the solvent molecules, and the nuclei will come down to the lower energy state. Another process is the spin-spin relaxation, and it is represented by T2. In this relaxation process, nuclei which are present in the higher energy state will lose energy equal to delta E to the another nuclei which is present in the low energy state. Now nuclei from the low energy state will flip to the higher energy state. So in one process, nucleus is releasing its energy equal to delta E to the surrounding solvent molecule, and another spin-spin relaxation process, nucleus which is present in the higher energy state loses its energy equal to delta E, that is the energy difference between the two energy level, to the nuclei which is present in the low energy state, and the nuclei which gains energy flips to the higher energy state. Now from these two processes, it is very clear that the net absorption of energy will take place when there is spin lattice relaxation. In the NMR spectrum, sometimes we see very broad signals and sometimes we see very sharp signals. The sharpness and the broadness of the signal depends upon the relaxation time, that is T1 and T2. If T1 and T2 are large, then we get the sharp spectral lines, and if T1 and T2 are small, then we get broad signals. There is a uncertainty principle. In this form we can take up, that is the product of delta E to delta T is equal to h by 2 pi. Now this can be modified in terms of frequency. Product of delta T and delta nu is equal to 1 by 2 pi. Now 1 by 2 pi, it is a constant. So from this equation it is very clear that if the relaxation time is large, then the signal will be sharp, delta nu will be small, that is the signal will be sharp, and if delta T is small, then delta nu will be large, that is the signal will be broad. The sharpness and the broadness of the signal also depends on the viscosity of the sample or the solvent used. If your sample is non-viscous and the solvent used is non-viscous, then the T1, that is the spin lattice relaxation, will be very large because there will be random orientation of the solvent molecules, and T1 will be large and the signal seen will be very sharp. At the same time, if the solvent or the sample liquid is very viscous, then the T1 will be small and the signal will be very broad. As I've told you that we get lot of information from NMR spectrum. A typical NMR spectrum shows different lines. In NMR spectrum, these are known as signals. We get different number of signals. The signals are present at different positions. So what the number and the position indicates about the structure of any compound. So very first thing is the number of signals. The number of signals tells us how many types of protons are there in the molecule. That is number of non-equivalent protons in a molecule. Second thing is the position of signal. where it is present in the NMR spectrum. This tells us what kind of protons are present in the molecule. Here the what kind means what is the magnetic environment around the proton. So position of signal is indicative of type of proton in the molecule. Third is the relative intensity of the signal. This shows the ratio of equivalent proton. Then it is a very important splitting of the signal, that is spin-spin coupling. You see there is one signal which is split up into different peaks, and this splitting tells us the number of protons on the neighboring carbon atom. So we get so much information from NMR spectrum regarding the how many types of protons are present, what type of protons are present, ratio of the equivalent proton, and at the last but not the least, that the number of protons present on the neighboring carbon atom. We will discuss now about number of signals. See the example methane, ethane, and propane. The NMR spectrum of methane shows only one signal. NMR spectrum of ethane shows only one signal, whereas NMR spectrum of propane shows two signals. So what is the meaning of that in methane only one signal, ethane only one signal, propane there are two signals? So as we know that the equivalent protons shows the absorption at the same place, shows the absorption at the same applied magnetic field. And if the protons are equivalent, if they are showing the absorption at the same applied field, then we say the protons are equivalent. It means to say that in methane all the 4 protons are equivalent. Similarly, in ethane also all the 6 protons are equivalent. But in propane, I have designated here some protons by A and 2 protons by B. It means to say the 6 protons which are designated by A, they are showing the absorption at the same applied field, whereas proton designated by B, they are showing the absorption at some other applied magnetic field. So 6 protons in propane, they are equivalent. 2 protons, they are equivalent, but proton A and B are non-equivalent proton because they are showing the absorption at different applied field. So the number of signals shows that how many equivalent protons are present in the molecule. So in methane, only one signal is seen. Then it shows that all the 4 protons on methane are equivalent. The spectrum of ethane shows only one signal, that all the 6 protons present in ethane are equivalent. And in propane, we see 2 signals. It means to say that it shows 2 type of protons. They are non-equivalent protons, and 6 protons are equivalent and 2 protons are again equivalent, but A and B are non-equivalent proton. So the meaning of equivalent and non-equivalent here means they are chemically equivalent and chemically non-equivalent proton. We will discuss chemically equivalence and chemically non-equivalent in detail in further slides. This is NMR spectra of a particular compound. By looking at the spectrum, we can see 2 distinct signals. So it is very clear that this particular compound must be having 2 different type of non-equivalent protons. So we can say that in ethyl chloride, their methyl group protons are equivalent, methylene protons B, they are equivalent, but methyl protons are and the methylene protons are non-equivalent. Therefore, in this compound, it shows 2 signals. So the number of signals indicate how many types of non-equivalent protons are present in the molecule. Another example we can see of isopropyl chloride. You see, A and A are the methyl protons and B is the methane proton. Methyl protons are chemically non-equivalent to the methane protons. Therefore, methyl protons will give only one signal. They will show the absorption at the same place, whereas B protons, methane protons, will show the absorption at another applied magnetic field. Therefore, the NMR spectrum of isopropyl chloride will show two signals. See some more examples. NMR spectrum of this particular compound shows three signals. It means to say that in this particular compound there are three types of protons are present. So there can be, it is a 1-chloropropane. Methyl protons here are different from methylene protons. There are two methylene protons. So B methylene protons are different from C methylene protons. They are chemically non-equivalent protons. Therefore, methyl proton will give one signal, methylene proton B will give one signal, and the methylene proton, which is attached to chlorine atom, will give one signal, different signal. It will show the absorption at a different place. So by looking at the NMR spectrum, we can say that there are three types of protons are present in the molecule. Three types means they are chemically non-equivalent protons are present in the molecule. Another example is this spectrum. There is only one signal, that is, in this particular compound, all the protons which are present, they are equivalent protons. See the example of tertiary butyl bromide. Although there are 9 protons, but they are present in the chemically equivalent situation. Therefore, they produce one signal, that is, they show the absorption at a particular applied field. Therefore, in this there is only one signal. So by knowing the number of signals, it tells us how many types of protons are there in the molecule. So one signal represents only one type of proton. Three signals represent three types of proton. So like this, by looking at the NMR spectrum, we can identify how many types of protons are there in the compound. See how we can identify equivalent and non-equivalent proton. Take the example of methane. In methane, there are 4 protons, and we don't know whether these are equivalent proton or non-equivalent protons. So we will substitute proton by any substituent Z. Here I have taken substituent Z equivalent to bromine. So all the 4 proton turn by turn will be substituted by bromine, and we will get the methyl bromide. And we know that in nature only one isomeric methyl bromide is present. There are not 4 types of methyl bromides. So we say all the 4 protons in methane are equivalent protons. Now take the example of ethane. Apply the same mechanism. Substitute every proton turn by turn by any substituent Z. Here the substituent Z is equivalent to bromine. So we get ethyl bromide, but again we get only one isomeric ethyl bromide, not 6 types of ethyl bromide. So we see that all the 6 protons in ethane are equivalent. So when the replacement of any number of protons give the same product or the enantiomeric products, then the 2 protons are chemically equivalent protons. This is the NMR spectrum of ethyl chloride. It shows 2 signals. One signal because of methyl protons, another signal due to methylene protons. Now we have to identify, we want to ensure that the two type of protons, methyl and methylene protons, are non-equivalent protons. So we will replace methyl protons by a substituent, say chlorine, and by the substitution we get the product 1,2-dichloroethane. Now the two methylene protons turn by turn are replaced by a substituent chlorine. So we get the product 1,1-dichloroethane. The two products obtained by the substitution are 1,2-dichloroethane and 1,1-dichloroethane. The names are different. Their names are different. It means there are two different type of compounds are obtained. Therefore, methyl protons and methylene protons are non-equivalent protons, whereas all the three methyl protons are equivalent. The two methylene protons are equivalent, but methyl protons and methylene protons are non-equivalent protons, and they will show the absorption at a different magnetic field. Therefore, in the NMR spectrum of ethyl chloride, we get two signals. This is the NMR spectra of N-propyl chloride, and this shows three signals. One signal is because of methyl protons, one is because of methylene protons, another is also because of methylene protons. Now we will see that all the protons present in N-propyl chloride, they are non-equivalent protons. So start with methyl protons. Substitute methyl protons by a substituent, say chlorine. So the product obtained will be 1,3-dichloropropane. Now in turn replace the methylene protons, center one, with chlorine atom. Then you will get 1,2-dichloropropane. Now replace methylene protons C by chlorine. It will give 1,1-dichloropropane. So all the three compounds obtained have different names. It means they are the different compounds, and therefore in N-propyl chloride there are three non-equivalent protons are present, and they will give three different signals. They will show the absorption at different magnetic field. Now there is a question about whether the two methylene protons of B are equivalent or they are non-equivalent protons. Now when we substitute methylene protons by, say, a substituent chlorine, then we get the stereoisomers. The central carbon becomes the stereocenter. In one isomer, halogen atom is present on the right hand side, and another isomer, stereoisomer, halogen is present on the left hand side, and they are the mirror images of each other. So they are the enantiomer. Enantiomers are the stereoisomers which are non-superimposable mirror images. So whether the NMR is capable of distinguishing between the enantiomeric protons or not. In presence of a chiral solvent, you can distinguish between the enantiomeric protons, but in presence of a chiral solvent, these two enantiomeric protons will give the same signal. They will show the absorption at the same position. So in a chiral medium, the enantiotropic protons are equivalent protons, whereas in chiral medium, the enantiotropic protons are non-equivalent protons. See the two methylene protons of 1,1-dichloromethane. The two methylene protons are homotopic protons because the substitution of these protons by any substituent Z gives the identical products. So these two protons, methylene protons, are chemically equivalent protons, and they are known as the homotopic proton. Similarly, in this compound, that is the 2-methyl propene, the two protons which are encircled are replaced by Z, and they produce the identical compounds. Therefore, these two protons are also identical. Methyl protons are different from the vinyl protons. So this compound, that is a 2-methyl-1-propene, will give two signals, one due to the 6 equivalent methyl protons and another because of the 2 equivalent protons. This is a very interesting example, vinyl chloride. The NMR spectrum of vinyl chloride shows 3 signals. It means proton A, proton B and proton C are non-equivalent proton. The proton A and B are the geminal protons, and we have to see whether the two geminal protons are equivalent or they are non-equivalent protons. So the same procedure is adopted. Replace proton A by substituent Z and proton B by substituent Z. You get two isomers, and these are the geometrical isomers. One compound is cis, another is trans. So the two isomers are different, they are not identical. Therefore, we can conclude that the two geminal protons present in vinyl chloride, they are non-equivalent proton. And these two protons are distereotropic protons. So NMR is capable of distinguishing between the distereotropic protons. They are the non-equivalent protons. So in vinyl chloride, we get 3 signals. Now we can summarize that homotopic protons, whether the medium is chiral or achiral, they will be chemically equivalent protons, and they will show the absorption at the same applied magnetic field. Whereas enantiotropic protons will be equivalent proton in achiral solvent, whereas enantiotropic protons in presence of chiral solvent will be non-equivalent proton and can be distinguished by NMR, whereas the distereotropic protons are non-equivalent proton and they can be distinguished by NMR. 1,2-dichloropropane is another very interesting example. A careless review of this compound indicates the presence of 3 NMR signals in the spectrum. But actually, the NMR spectrum of 1,2-dichloropropane shows 4 signals. So we can arrive at the 3 signals, one because of methyl protons, second because of methylene protons, and one because of methane protons. But the fourth, from where the fourth one has come? Now the 2 methylene protons are non-equivalent protons here. Replace each methylene proton by Z and you will get the 2 products which are not the enantiomers. One can argue here that perform rotation at carbon-carbon single bond between carbon number 1 and carbon number 2. Then you will get the mirror image of structure 1. So the 2 will become enantiomers. But remember that we have represented here chemical structure in Fischer projection formula. And Fischer projection formula are eclipse structures. They are not the staggered structures. So when you rotate at single bond between carbon number 1 and 2, it will become staggered. So you cannot write Fischer projection formula of a staggered structure. So any type of rotation at carbon-carbon single bond will not produce enantiomers. So the 2 protons, methylene protons, are diastereotropic protons. The compound forms are diastereoisomer and the 2 protons are diastereotropic protons. And we know that NMR can distinguish between diastereotropic protons. And that's why in NMR spectrum of 1,2-dichloropropane, you see 4 signals. Now, for the further reading, you can consult Organic Spectroscopy by William Kemp. Another book is by Introduction to Spectroscopy by Pavia, Lefman, and Chris. These are very good books, and if you study these books, you will gain a lot of knowledge. And I will tell one thing here, that spectroscopic techniques are very, very important. If you go for some interview and you answer all the spectroscopic questions, and along with the spectroscopic techniques, if you are thorough with the chromatographic techniques, you will be picked up by any industry, because these two things are very much used in industries. So with this, I conclude my lecture.